Now that I've introduced both the activity and the excess property approaches, and we're now going to unite the two approaches by looking at the chemical potential equation. So for the activity, I wrote out that the chemical potential is equal to the standard state chemical potential plus RT and the activity coefficient, or activity, A sub I. For the excess property approach, I wrote out that the chemical potential was equal to the standard state chemical potential plus RT ln of xi plus some excess partial molar Gibbs energy. Both sides have the standard state chemical potential that cancels out. And what we could do is we could rearrange the equation so that we just have A sub I on the left-hand side, and on the right-hand side, we're just going to have xi exponential of our partial molar Gibbs excess over RT. Okay. All right, and so essentially what we have now is for our activity, it's essentially just going to be the mole fraction of species I times some term that accounts for or describes non-ideality in the mixture. And so what I'm going to do now is I'm going to define a new term, gamma sub I, which I'm going to call the activity coefficient. And for this gamma sub I, it's just going to be equal to that exponential of the molar Gibbs excess energy over RT. And so it's through this activity coefficient that we account for non-idealities in our mixture. We could also rearrange the equation equivalently. We could say that our partial molar Gibbs excess is going to be equal to RT ln of gamma sub I. Okay? All right, and so I wrote out all these equations. But now let's kind of summarize, all the new terms that we learned and how you could think of them. So this activity, the way I think about it, it's just an effective mole fraction. So if we go back up here, if xi is the actual mole fraction, actual composition of species I in the solution, due to non-idealities, that can affect its influence, its total influence in the solution. And so the activity is basically a descriptor of how species I affects the mixture. Okay? All right, and so if we have an ideal solution, we find that A sub I is basically proportional to X sub I. But if we're dealing with non-ideal solutions, we find that the activity becomes a sort of nonlinear function of X sub I. Okay? And then this activity coefficient, gamma sub I, is just a parameter that quantifies how non-ideal the solution is. Of a mixture. And so typically, if you plotted your activity versus X sub I, you would see it's a very nonlinear equation, or not a straight line essentially. Okay, but there are going to be two limits. So at the limit that xi is 0, or when xi is equal to 0, your activity is 0, and when xi is equal to 1, your activity will also be 1. But in between, you could get many different shapes. So here's one example, but not the only example. Okay. And so the way to think about this plot is if you had an ideal solution, you would just expect a straight line like this. So ideal solution. But with a real solution, a non-ideal solution, you see that it deviates from that straight line. Okay. As I mentioned before, in the limit that x of I goes to 1, your activity should also go to 1. But in the limit that xi is very small, we see here that the activity should be proportional to x of I. And that slope that we get there the slope that we get here is what we call the infinite dilution value. Infinite. Okay. And so the way to think of it is like this. The infinite dilution value at some temperature is equal to the limit of gamma sub I of some temperature, pressure, and collection of mole fractions. So it's the limit of it as xi goes to 0. Okay. All right, and so once again, if we think back to Henry's law, we saw that our activity coefficient was equal to hi over p times xi. And so that would mean that our infinite dilution gamma is just the Henry's constant over total pressure. Okay? All right, and so depending on the model you use for the activity coefficient, you could have varying relationships with the mole fraction xi. But generally, it'll be somewhere between these two limits. So at xi is very small, the infinite dilution limit, you get gamma infinity. And when xi is basically 1, you get that your activity coefficient's also 1. And somewhere in between, you'll see that your gamma sub I value will change.